Okay, whenever we are going to solve any numerical, first we have to write what is given there. Okay, so I'm going to solve here given. Okay, what is given? See, a solution of 10 gram beta. Yes. Okay. So first we have to write the given part. So what is given here? A solution of 10 gram. Okay, of the non-volatile, non-dissolving compound. Okay, that means it is solute. And solute is what it is? W2. Mass is given. It is 10 gram beta. 10 gram. Okay. Dissolve in 0.220 kg of solution. Okay. Benzene. Benzene means the solvent. It is solvent beta. So if it is solvent, then it is W1. So W1, it is given in 0.200 kg, but we want to have in gram. So for that we have to multiply it by 1000 gram per kg. So kg and kg will get cancelled. Now we will get answer in gram. So 1000 into 0.2 will be 200 gram. So now we have W1 equals to 200 gram. Got the answer, that one? Next, everyone keep replying. Benzene boils at 81.2. Okay, the solution boils at. So it is T solution. I'm just taking boiling point of solution is, I'm just taking TS, or we can write T2 also. This T2 equals to how much? It is 81.2 degrees Celsius. Okay, then calculate the molecular weight of the compound. That means we have to write to find here. To find. What do we have to find? Capital M from the formula. Okay. Then it is given ebullioscopic constant, means Kb is given beta. Kb. How much? 2.53. Okay, it is 2.53. Boiling point of pure benzene is given. So T0 is also given, or you can take T1, 0. Okay, which is 80.1 degrees Celsius. Okay. And M we had to calculate. Now we have formula. Formula. We have derived that also, which is capital M or M2 or M also is equals to 1000 into Kb into W2 divided by we have delta Tb or del Tb into W1. This is the formula. Okay, everyone. We had derived that data. Okay. Now we had to place the value. See, we do require del Tb. So first let's calculate delta Tb. So delta Tb equals to we have T2 minus T10 beta. So T2 is what? It is 81.2 minus T0 is 80.1. So if we will solve, so we will get delta Tb equals to 1.1 degrees Celsius. Understood now? Now we have to solve. Now, solution I'm writing here. Solution. Okay. So M2 equals to 1000 into Kb. Kb is how much? It is given that one. 2.53. 2.53 into W2. W2 is that one. 10 grams. So I'm writing here 10. Divide by. We have what we have? Delta Tb. It is 1.1 into W1. W1 is what it is? 200. So I'm writing here 200. So here 1 0 and that 0 will get cancelled. That and that 0 will also get cancelled. Now if you will multiply 100 into 2.5, sorry, 2.53, so it will be 253 beta. Divide by 1.1 into 2 will be 2.2, right? Everyone, 2.2. Is it everyone?
Yes, sir.
Or we can write M2 equals to, now we don't want to have that point with us. So what we can do? We can do like 253, or we can do one thing, one more step we can calculate here only, beta. Wait. We will simplify that more. Okay, how? See, that 2 and that 100 will get cancelled by 50 times now, right? Is it?
Yes, sir.
Yes, sir.
Yes. So now we have 5 threes are 15, will be 5 here, and 1 0 we have to write because we have 15. Then 1 will carry here, 5 into 5 will be 25, and 1 26 will be 6 here, and we have 2 carry. 5 twos are 10 and 2 12. So we have 12. And now after 2 point, we're gonna have point here. Divide by 1.1. If we will solve, okay, that point can shift over here, and or we can write that point also we have to shift here. So we can write that in simple form: 1265 divided by 11, right? Everyone. Okay, now we have to solve that beta. So it is 1265 divided by 11. So 11 1 is 11. Subtract that, we have 1 remaining. Then we have to use that 6. Again 11 1 is 11. Again we have to subtract. Now we have 5. Then we have to use that 5. So 11 5s are 55. So now it will get cancelled. Okay, now we have 115 answer. So M2 equals to, M2 will be what? 115 point, oh, no, 0, or you can use 115 only, and unit is, the unit of molar mass is gram per mole, and this is the answer. Okay, everyone?
Yes, sir.
Yes. Freezing point is what? It is the temperature at which the vapor pressure of liquid becomes equals to the vapor pressure of solid of that particular compound. Okay, like if we discuss about vapor pressure of water, so we have to compare vapor pressure of water with the vapor pressure of ice. Okay, like this. Okay, so it is the temperature at which the vapor pressure of liquid becomes equals to the vapor pressure of that liquid only, solid state of that compound is called as freezing point. Now, how freezing point depression takes place, that we have to understand. It is very important. Okay, so again I have to move the screen. Okay, so let's understand how it takes place. Again, we have to take one container that we discussed for elevation in boiling point. So here we have one container. Okay, someone is in waiting room. Banuri. Okay. Then again, we had to close that container beta like this. Okay. And here again we have taken what? This is what? Volatile solvent. Volatile solvent. Again, if it is volatile solvent, so it is going to evaporate as well as it is going to condense. And if we fix the temperature, again, if we fix the temperature like 25 degrees Celsius, constant. Okay, constant temperature of 25 degrees Celsius. So after some time, rate of evaporation becomes equal to the rate of condensation, and that is called as what? It is called as what? Equilibrium. So at equilibrium, vapor pressure applied by the vapor pressure of the liquid on that particular surface of the liquid is called as what? vapor pressure. Okay. Now we have to like freeze that pure substance first. Okay. So let's discuss about water only, beta. Only water we are going to discuss here. Okay. So we know freezing point of water is what? It is 0 degrees Celsius, na? It is 0 degrees Celsius. It is the freezing point of water, right? Is it everyone? Yes. And let's discuss here the vapor pressure at equilibrium at 25 degrees Celsius is what it is. No, at normal condition, but at normal condition, I'm just taking about normal condition. Here the vapor pressure is let 50 mmHg. 50 mmHg. Okay, and vapor pressure of ice is let it is 5 mmHg, beta. 5 mmHg. I'm just taking example, huh? Okay, that means at a normal condition from 25 degrees Celsius to ice condition, okay, liquid to ice, if you have to convert, we have to lower the pressure up to 45 degrees Celsius. No, 45 mmHg we have to decrease, right?
Yes, sir.
Yes. Okay. But when we are going, that means we have to decrease the temperature up to 45 mmHg. This is the task. And for that, we have to lower the temperature. Okay. Now, second instant. Now we have dissolved non-volatile solute. Non-volatile solute. Okay. If non-volatile solute is going to dissolve here, okay, again surface like non-volatile solute particle are going to acquire surface, rate of evaporation is going to decrease. That means finally vapor pressure is going to decrease, na? If vapor pressure is going to decrease, that means let that decreased vapor pressure is 45 mmHg. Okay, at normal condition it was 50 degrees, but due to addition of non-volatile solute, vapor pressure lowers to 45 mmHg, right? Is it everyone?
Yes, sir.
Yes. So when temperature, vapor pressure is going to decrease, so how much it is going to decrease? How we have to calculate? Again here, the freezing point temperature. Okay, I'm just taking TF beta, TF. Okay, it is for pure solvent, so I have to take 0 here. At the power, at the degree, we have to take 0 here. Okay, so with a freezing point temperature of pure liquid. Okay, I'm writing here freezing point temperature of, see, whenever we are adding degree here means 0 here means it is for pure solvent beta, pure solvent. Okay, so freezing point temperature of pure solvent. Okay, how much we have taken? Like for water it is, just take a fact, it is 0 degrees Celsius, na? 0 degrees Celsius. And for that, in order to freeze that, we have to decrease the pressure from 50 mmHg, 50 mmHg to 5 mmHg, now that we discuss now. Right, everyone? Is it?
Yes, sir.
Yes. But now we have added non-volatile solute here, beta. What we have added here? Non-volatile solute. See, vapor pressure. Now let's discuss about vapor pressure. Vapor pressure of pure water was, it is 50 mmHg. It is 50 mmHg, right? But when non-volatile solute is added here, then vapor pressure got lowered, na? Because some of the particle of non-volatile solute acquire space on the surface, due to which the rate of evaporation decreases, due to which number of vapors also on the container is going to decrease, and which leads to lowering of vapor pressure. So vapor pressure of solution after adding non-volatile solute is 45 mmHg, right, everyone? So what is the difference? The change in vapor pressure, it is 5 mmHg, na? Right, everyone?
Yes, sir.
Okay. Now we have to freeze solution now. Okay. So for solution, I'm writing in this particular side and using the different color so that you can differentiate easily. Okay, now we have solutions. Vapor pressure is 45 mmHg. Okay, and now we had to drop that vapor pressure up to 5 mmHg. Na? Right. See, here we had to decrease from 50 to 5 beta. So how much we had to lower? It is 45 mmHg. But in another case over here, we have to decrease from 45 to 5. That means here we have to lower the vapor pressure up to 40 mmHg only, right? Right, everyone? Is it? Keep replying,
Yes,
beta.
sir.
Okay. So now I am going to have some question for you. Now, water was used to freeze at 0 degrees Celsius. And for that, we had to decrease the vapor pressure okay, from 50 to 5 mmHg, means 45 mmHg we had to decrease, and for that we had to lower temperature. Okay, and it is 25 degrees Celsius to 0 degrees Celsius. It is for pure water. Huh? But what about solution? Here we do not have to lower temperature like pressure up to 45 mmHg. We have to decrease only 40 mmHg. That means we do not have to drop the temperature up to 0 degrees Celsius beta. So we had to lower temperature up to 25 degrees Celsius to maybe 2 degrees Celsius. We do not have to drop up to 0 degrees Celsius beta. We don't have to drop up to over here. Why? Because its vapor pressure already had decreased. So it will freeze before the freezing point temperature. That is called as depression in freezing point. We do require to reduce less temperature. Now, this effect is called as depression in freezing point. In boiling point, we gone through about elevation, so it was increases there, but here it is decreases. Understood, everyone?
Yes, sir.
Yeah. So this is the process, beta. This is the complete process how vapor pressure is going to lower. Okay. So now key point for the particular instant. So key point will be when any non-volatile solute added in a volatile solvent in order to form the solution, vapor pressure of the solution decreases. Due to decrease in vapor pressure of the solution, we do require have to like freeze that particular solution before the freezing point of the pure solvent. That lower that required less temperature in order to freeze the solution is called as depression in freezing point. Understood? Everyone understood, beta?
Yes, sir.
Okay, so let me show you. Okay, that numerical. Have you took a screenshot for the numerical? Everyone.
Done, sir.
Done now? Okay. And numericals are very important, beta. Okay. Over here. See, that delta F we already derived. Okay. Now, freezing point depression is a consequent of the vapor pressure lowering. See, due to lowering of vapor pressure, freezing point is getting depressed. Okay. So here we have like a graphical representation of how vapor pressure is going to lower and freezing point is going to depress. Okay, so the effect of dissolution of the non-volatile solute. See, whenever we are going to dissolve non-volatile solute, then that effect is going to show into the solvent on freezing point of the solvent can be understood in terms of the vapor pressure lowering. So here we have like solid solvent, and here we are going to when dissolve in water. So this is the liquid. This is a liquid solvent, means that condition is given for vapor pressure lowering. Okay, over here on y-axis, and temperature is given on x-axis. So see here, it is getting like freezes over here, beta. Okay, means we had to decrease the temperature up to here, so it is going to freeze over here. Okay, let this is for water 0 degrees Celsius. But when we are like dissolving non-volatile solute here, okay, So wait, I'm just erasing extra things. Okay, so it is that point is T0, means it is the freezing point temperature of pure solvent. But when we are going to dissolve non-volatile solute here, okay, it is going to lower up to here. Okay, that difference is called as depression in freezing point. So this is for the solution and this is for the pure solvent. Okay. Okay, now molar mass of solute from the depression in freezing point. What is the time, beta? Okay, time is also done. So we'll continue that mathematical expression for molar mass of solute from freezing point temperature. We will derive that tomorrow, na? Okay.
Yes, sir.
Okay, beta. Okay. So good night then.
Thank
Thank
you,
you,
sir.
sir.
Yeah. Bye. Good night.